Hey guys, how we doing? It's Mr. Chavla. In this video, I'm going to be going over the June 2019 Common Core Algebra 2 exam, numbers 25 through 32. That'll be the part 2 questions that were 2 points each. I went through the first 24 questions in the last two videos, 12 questions per video for the multiple choice. So this is the June 2019 exam for the part 2 key, numbers 25 through 32. And again, it's Mr. Chavla or Mr. C. All right, let's get started. Let's see what we got here. Number 25. The table below shows the number of hours of daylight on the first day of each month. So it's the hours of daylight on the first day of each month in Rochester, New York. So these values are not, this is just the number of hours of daylight on January 1st, February 1st, March 1st, April 1st, May 1st, June 1st, July 1st, August, September, and so on, right? Just the number of hours on the first day of the month. Now, before I look at anything else, given the data, what's the average rate of change? What's the average rate of change in hours of daylight per month from January 1st to April 1st? So we got January 1st, I'm going to use a different color right here, and April 1st right here. So it's going to be, the rate of change formula is the change in output divided by the change in input, right? So 1 for the first month of the year, January. This is 2, 3, April is the fourth month of the year. So it's going to be the change in months, right? Because it's per month. So per month, it'll be 4 minus 1 on the bottom, because April minus January, 4 minus 1. And then we have to subtract the hours of daylight. How much did that change by? 13 minus 9, minus 9.4, right? 13 minus 9 minus 9.4, you could use your calculator, but that'll become 4.5. And that's how much the hours increase, the hours of daylight, over 3 months. And that becomes 1.5 hours of daylight per month. I won't put the units because they already did. All right, so that is our answer to the first part of the question, okay? I'll just copy it down. It's actually better if you could see the table with it, right? So the average rate of change is right there. The hours of daylight per month increases by 1.5 hours on average each month. All right, so that was the first part of the question. We got the average rate of change in hours of daylight per month from January 1st to April 1st. Usually we have to put the units, but if they put it for us, we don't have to. Now let's go to the next part of the question. Interpret what this means in the context of the problem. What it means is that, very simply guys, as we went from January to April, we got the average rate of change, right? The number of hours of daylight, since it was a positive 1.5, increased from 9.4 to 13.9. Over the 3 months, it increased by an average of 1.5 hours per month. That was pretty simple if you knew what to look for. So, on average, the number, let me neaten that out. And we don't have to say hours twice. It'll become kind of redundant. So I'll just say the amount I'm trying to see how to word this. The number of, I'm going to minimize me for now, hours of daylight increased, and we got to remember to say on average, right? Somewhere in the problem. Or we could say it increased by an average of, right? Increased by 1.5 hours per month from January 1st to April 1st. Some version of that would get you full credit, all right? And I'll even Let's keep our notation consistent. All right, I'll even copy the work down here. So we had 13.9 minus 9.4. It's just a basic rate of change formula. 13.9 minus 9.4 over 4 minus 1. So I'm just copying it back down again here so you could see everything in one. Became 4.5 hours over 3 months. That became 1.5. And we put the unit in the second part of the question, all right? So now we have everything, all the answer. The full solution is here. So I copied it down here instead. So we got the average rate of change over here, and then the interpretation there. All right, pause the video if you need to. I'm moving on to number 26. It's all about rate of change, guys. Okay, solve algebraically for x. What I'm going to do is, so algebraically, obviously, we have to show work, and we need to solve for x. The first thing I'm going to do, guys, is remember the denominator cannot be 0 because you can't divide by 0. So I'm going to make sure we know what x cannot be. 2x in the denominator cannot be 0, and x plus 1 in the denominator can't be 0. So if I get an answer of 0, because 2 times 0 is 0, or x equals -1, those have to be rejected. So I want to make sure if I get any of those answers, I'm going to either I did something wrong, or I didn't do anything wrong, but I need to reject it. But what I will do is I'm going to rewrite the equation now with some space in between, and you'll see why in a second. Because I'm going to make all the denominators the same so that we could then get rid of them. So here's what we got now. First thing, I don't have an x plus 1, so I'm going to multiply x plus 1 everywhere. That means on the top and the bottom. Because whatever I do to the bottom, I must do to the top. Now, let me actually start that over. There's an easier way to do this first. Sorry about that, guys. I just want to make this as clear and simple as possible because there were so many ways to do this. There's a 4 here and an x here. I can make both the denominators here equal to 4x by multiplying x on both sides here on the right hand side. And if I double the values here, and remembering that whatever I do to the top, I must do to the bottom. Then this top one becomes 14 over 4x. When I multiply by 2 by 7, I get 14. 2 times 2x is 4x. Minus 2 over x plus 1 equals 1x, or just x, over 4x. So now that 1x is the same, right? There are so many ways I could proceed with this, but why not just continue to make the denominators the same? Now, if I just multiply 4x here, because that's what's missing, and we're missing x plus 1 here, we could have done it in one step, but I wanted to make it easier to see. Now the LCM, all of these have a denominator of 4x times x plus 1. So all I care about now is the numerators, all right? So if I distribute 14, I'm just going to use the numerators now. 14x plus 14 minus 4x times 2 becomes minus 8x equals, I don't need this 1 anymore, so it's just x times x plus 1, which when I distribute, I get x squared plus 1x, or just x. I'm going to add 8x to both sides, or first, I'm actually going to combine like terms. 14x minus 8x is 6x. So this becomes 6x plus 14 equals x squared plus 1x. I'm going to subtract 6x on both sides, and I'm going to subtract the 14. Since there's no like terms, I could either put a plus 0 here or leave it blank, and that just comes as down as minus 14 here. These terms cancel out. I get the left-hand side equal to 0. I get x squared 1x minus 6x minus 5x. Let's solve by factoring. Which two numbers multiply to negative 14 and add to negative 5? Negative 7 and 2. So it'll be x minus 7, x plus 2 equals 0. Negative 7 times 2, negative 14. Negative 7 plus 2 is negative 5. So if x minus 7 is 0, I get x equals 7. If x plus 2 is 0, I get x equals negative 2. And I want to make sure that none of my answers were equal to 0 or negative 1. 7 is not equal to either of those two, and neither is negative 2, so this is my solution set. My two solutions are x equals 7 and x equals negative 2. I could use the calculator to confirm, so let's do it. Let's actually confirm in the calculator, because I want to make sure you guys know how to do this. So this is me uploading the previous video I made for the multiple choice in this exam. So I'm going to go to my Desmos calculator. And I'll actually go to I could go to the graph, or I could use the regular one. Doesn't matter. I'll use the regular calculator and the original equation. I changed my mind. I'll use the graphing calculator because you'll see why in a second. So y1 is equal to 7 over 2x minus 2 over x plus 1. What do I want y to equal? Of course, I want it to equal 1/4. I could even enter it like this, guys. You see how the equation is equal to 1/4 in the OneNote? I'll make it equal to y1 here. So that way, when I enter a table, if I get y1 equals 1/4, I know I got the correct solution. So x and y1. Let me see if it works if I put the y1 last. So like if I put 0, 1, I have to put the y1 first. y1 equals, so we got, see how I said when it's equal to 0, it can't work, it's undefined, and when it's negative 1, it's undefined. So we did do that correctly. I just like to put them in order. So all I'm going to do is I'm going to check the two numbers now. Negative 2 results in 0.25, which is 1/4. 7 also results in 0.25, which is 1/4. So that was a quick way to check that we got the correct answers. So that was all there was to it, guys. Now I need to find my marker because I just dropped it and I don't know where I put it now. Found it. I was sitting on it. Okay, so I'm gonna pull up the solution here so you could see it, right? Make the screen a little smaller so we could see everything. Hopefully it's not too small, and it seems like there's some room for me too here. I'm back. Hi. Okay. And pause the video, take a screenshot, do what you gotta do. We're moving on to number 27. Let's go! Ooh, look how much space I had left over there, guys. They gave you a lot of space. I guess I was scrunching it into that screen so I could fit it all in one spot. My mom's cell phone's ringing. I'm at my mom's place. She left her cell phone here. Anyway, next question, 27. Graph f of x equals log base 2 of x plus 6 on the set of axes below. So, if you know your logs really well, you know it's going to have an asymptote at x equals negative 6, meaning the graph will never cross that. But I'm going to start by first just putting, wrong window. I'm going to start by putting the equation in the graphing calculator. And we'll use a set of ordered pairs. And I'm going to minimize me again, sorry. First thing I'm going to do is I'm going to set the equation. Not the equation, I'm going to set the graph settings, which you should know how to do for yours too, right? So it just goes from negative 10 to 10. And that graph that we have there was from the previous question, so we're about to take that off. And we want to always start with this standard setting, right? Every calculator should have a standard setting that where you could set the x from negative 10 to 10 and do the same for y, right? Now what I'm going to do is I'm going to enter that equation. It was f of x equals log base 2. So what I love about this calculator is you could actually just enter f of x. You can't do that in every calculator. And I'm going to make sure that I could get log base 2 of x. Miscellaneous, log with the given base. So log base 2 of x plus 6, and that's all there was to it. Okay, so then the next thing. So first thing I want to do now, guys, I want to analyze the shape of the graph. You see how it continues to... I just messed everything up. Let me fix that. I messed up the setting. I changed it by mistake. All right. Okay. So now, if I look at the graph, guys, Okay, sorry. If I look at the graph, what? Okay, see how it has an x-intercept at negative 5, 0? It gradually decreases, right? And it approaches negative 6, but x never reaches negative 6, right? X never reaches negative 6. It just gets closer and closer because it has an asymptote there. And here's the y-intercept. And what I want to be able to do is get a few points and then sketch a graph, all right? So now I'm going to use the table, keeping in mind that the graph approaches but never reaches negative 6, which I could confirm in the table. So I'm going to enter table x, f of x, right? And I'm going to start, let's say I started at negative 10, right? See, it's going to be undefined because you can't have an x value, you cannot you have to start greater than negative 6, right? So a lot of people, the mistake they make is they start at the y-intercept, but they forget that the graph has to approach the x equals negative 6, because everything above negative 6, so even negative 5.9 works, guys. Negative 5 point, I'm just putting in random numbers, I don't know. 5.75, negative 5.5, negative 5.25, right? I'm just putting in some numbers just so you guys understand that it doesn't start at x equals negative 5 and it doesn't stop there. Okay? You have to understand there's an asymptote. It gets closer and closer to negative 6 but never touches, right? It gets, the closer I get to negative 6, the lower the graph goes until it approaches negative infinity, right? And that basically is so close to negative 6 that it doesn't work, right? So negative 5.8 I'll put. Negative 5.9. Okay, enough with that. Now the rest I could use a scale of 1, negative 4, negative 3, negative 2. Now I have to enter it one by one because it didn't realize that I wanted to continue like that. And you see here it begins to increase very slowly. So what I'm going to do is I'm going to, the most difficult part is just making sure I get my end behavior correct. That means that as x approaches negative 6, the graph approaches 0. I mean, the graph has an asymptote, so it gets closer, but never touches where x is negative 6. So 1, 2, 3, 4, 5, negative 6, right? So it never touches negative 6, so let's knock that part out of the way. Negative 5.75, negative 2, that's like 3/4 of the way. Negative 5.5, negative 1, that's halfway. And then the rest is pretty easy. I don't need to put the negative 5.25. I'll even erase that so that I don't have to deal with it anymore. And let's just deal with the rest of the graph now, which will be much easier. Negative 5, 0 is an x-intercept. I'm trying to make it so that I'm not blocking anything. So I'm trying to get this to stay here. So how would I get it to stay without it? Okay. Oh boy, I'm sorry guys. I'm like struggling to keep this all in one window. Okay, so I'm going to graph it. Negative 5, 0, negative 4, 1. I'll even label the y-axis here 1. And here we have negative 4. Negative 3 is about 1.6, a little over 1.5. Negative 2, we get 2. And I'll even label them occasionally. Negative 1, we get 2.3 something, basically just a little less than 2.5. The y-intercept is about 2.6, which is a little more than 2.5. Then 1, we get 2.8, so we're just staying up here. 2, we get 3, so that's up here. When x is 2, we get y equals 3. I won't even put that because it's just not going to work. Okay, so when x is 2, we could label the x-axis. The y-axis I don't want to label up here because I don't want it to get confused with the graph. So when x is 2, wrong one. Yeah, guys, I'm kind of struggling with the calculator here. So when x is 2, I get y equals 3. At 3, I get like 3.2. I'm not going to bother with that. 7, at like 5 or 6, at about 5, I get about 3.5. So 3, 4, 5, 1, 2, 3.5-ish. All right, because I don't really need to graph that closely. Then at 10, I get 4. So 6, 7, 8, 9, 10. And the rest is just details. This is where it goes up to. And now I'm going to connect it, and the one thing I got to remember to put is my arrows and going through these points carefully. Sorry guys, I messed that up. Okay, so let's get this going. So I'm going to stop, and then the one thing I want to remember is to put the arrow here. All right. Connect. All right. Now the thing is, like, when you fill the entire grid, you don't have to put an arrow at that point. So I won't even put that there. I just learned that recently. But you want to make sure all the points that are lattice points, meaning like where the x and y are both integers, or where like it would be on a corner grid. So like -5, 0, you want to make sure that's labeled properly. -4, 1. You want to make sure that that's clear, right? So that if the graph doesn't go through it perfectly, at least you labeled all the points. -2, 2. All right, we got that. Then we got 2, 3. And then it went up to 10, 4. All right, that's all there was. And typically I would put the arrow on both ends, but I learned that when you fill the grid, so we reach the outermost portion of the grid on the right-hand side, we don't have to put an arrow there. Okay, it said to graph the function on the set of axes below. We did it. And this is our asymptote, which we didn't have to sketch. That's why there's an arrow. You see how the graph never touches or gets up to the line where x equals -6, okay? So that was it for that one, guys. We're going to move on to the next question. Given tangent theta equals 7/24, and theta terminates in quadrant 3, determine cosine theta. Okay. Let's just work this out. First thing, we have our quadrants. Here's 1, 2, 3, 4. If you remember the acronym, add sugar to coffee. We're in quadrant 3. All positive in quadrant 1. S, only sign positive in quadrant 2. T, only tangent positive in quadrant 3. So cosine theta will be negative in quadrant 3. All right? Then what we're going to do is we're going to use the acronym SO Ka Toa. Now I would have drawn in the coordinate grid, but we could just draw any simple right angle to keep it simple, right? So if our angle theta is here, right? And here's a right angle. We need a triangle. This means tangent theta is equal to opposite over adjacent. The opposite is 7. So opposite from theta is 7. Adjacent to theta is 24. Now we have to find cosine theta is equal to adjacent, that's A, over hypotenuse. But we don't know what the hypotenuse is. So we need to find the hypotenuse. So we're going to do 7 square plus 24 square equals C square. I'll just call this C for the hypotenuse, right? The Pythagorean theorem. We know 7 square is 49. 24 squared, I do not feel like doing that in my head right now. So let's just use the calculator and find out what 24 squared is. $576. Y'all saw that? So plus 576 equals C squared. Sorry if this was kind of messy. And then we're just going to add 576 plus 49. Or 49 plus 576, 625. So 625 equals c squared. We take the square root on both sides. And since length can't be negative, it will take the positive square root, right? So I'll just do this. Square root of 625 is just 25. So our hypotenuse is 25. So c equals 25, or 25 equals c. So then remember, cosine of theta has to be negative. So cosine theta, our final answer, is equal to adjacent, which is 24, over hypotenuse, which is 25, but it'll become negative 24 over 25, okay? So this is our final answer. That was kind of a lot for a 2-point question, but we got it. So I always like to check to make sure we hit everything. So tangent theta is this. Theta terminates in quadrant 3. That's why cosine is negative. Find cosine theta. We definitely did it. Okay? Pause the video if you need to. I'm moving to 29. I think we're about halfway there. And I'm going to pull me up for a little while too. Okay, here I am. So, Kenzie believes that for x is greater than or equal to 0, the expression 7th root of x squared times the 5th root of x cubed is equivalent to the 35th root of x to the 6th. It seems like what she did was she multiplied the roots and said, okay, 7 times 5, excuse me, hiccups. 7 times 5 is 35th root, and 2 times 3 is 6 exponent. Now, I'm pretty sure that's not how it works, but let's just prove it that it doesn't work. It says justify algebraically. So is she correct, yes or no? Justify your response algebraically. Well, we'll do that. So if I start with x squared, 7th root of x squared, when I have a radical symbol, this is the same as x raised to the exponent goes in the numerator, the index or the root goes in the denominator. This is the same as x to the 7th times x to the, so 5th root of x cubed, using the same rule, is equal to x to the 3/5 power. Okay? So what I'm going to do is I'm going to, remember, when you multiply exponents, if you multiply 2 by 3, you get 6, and that's how she got that. You multiply 7 by 5, and you got 35, but that's not how it goes. When you multiply two bases, when the bases are the same, you have to add the exponents. So this becomes x to the 2 over 7 plus, that was too messy for my liking. Let me try that again. 2 over 7 plus 3 over 5. And I'll bring down the equal signs. When you add the exponents, and I'm just going to use the calculator because I don't feel like doing it by hand right now, when we have the tool handy, and I'm going to minimize me again. 2 over 7 plus 3 over 5. We get a decimal, but no problem. If you know how to change it back to a fraction in your calculator, you're at an advantage, all right? It's x to the 31 over 35, and I just misplaced my pen, found it. So x to the 31 over 35. Okay, this becomes x to the 31 over 35. If we convert this back into radical form, we insert the radical symbol. The denominator of the exponent becomes the index or root. The base goes in the radical symbol. And then the numerator of the exponent, which is 31, is the power, right? So since this is not equal to these two are not equal, we're going to say no. Kenzie is not correct, and we justified our response very much. All right, so we follow down We got that it's equal to x to the 31 over 35, which is equal to the 35th root of x to the 31, and not the 35th root of x to the 6th. All right, so these two are not equal. I'm circling them so that they know what we're pointing to. So the answer is no, because of this. All right, enough with the arrows. Okay, we've really justified our response. Moving on to number 30. When the function p of x, and I'm going to pull back up here. Hey, okay. All right, when the function p of x is divided by x minus 1, so p of x is divided by x minus 1, the quotient, which means the result you get when you divide, is x squared plus 7 plus 5 over x minus 1. Now guys, when what am I trying to say? I don't know what I'm trying to say. I've gone crazy. When you get a quotient and you have a number at the end, the 5 on top of the x minus 1, that 5 is the remainder. Just saying. Remember, if you've divided polynomials, you'll know how that goes. So there were a few ways to do this. One of the ways is just to multiply both sides by x minus 1. So if I multiply both sides by x minus 1, I'll do it like this. So p of x is going to end up equaling x squared plus 7 plus 5 over x minus 1, all multiplied by x minus 1. So that's the same as if I were to distribute individually. So first I'll distribute the x squared over x minus 1. And that'll become x cubed minus x squared. Then I'm going to distribute the 7 over x minus 1. That becomes plus 7x minus 7. Now, what I'm not going to do is I'm not going to distribute the 5, because if I take positive 5 over x minus 1 and just multiply it by x minus 1, the x minus 1 and the x minus 1 cancel out, because you divide them by itself and it cancels. Beautiful. All right, so now what we end up with is p of x equals x cubed minus x squared plus 7x minus 7 plus 5. And remember, they said to state it in standard form. So all I have to do is combine the like terms, and I should be good to go. P of x equals x cubed, no like terms, minus x squared, no like terms, plus 7x, no like terms. Negative 7 plus 5 is negative 2. And that, my friends, is our final answer, with me wanting to neaten out this equal sign because I didn't like the way it came out. Whew, perfect equal sign. Okay, now I'm going to minimize. I don't need to minimize anything. We got everything here. All that we need is right here. Even me. Okay, make sure you got this. Take a screenshot. Do what you got to do. This is a complete and correct response. We're almost done, guys. 2 more questions. Number 31 and 32. Coming up. Whoop. Wow, look how much space I left. Okay, I like this one. Given the write a recursive formula for the sequence 6, 9, 13.5, 20.25. Recursive formula always involves stating the first term first. So A1 equals 6, not an explicit formula. Then we have to see what's the pattern. 6 plus 3 is 9, but 9 plus 3, not 13.5. That would have been 12. So it's not a plus pattern, it's a times pattern. And the way to find out quickly, guys, is divide the 9 by 6. I have to minimize me. I'm going to take out the graphing calculator for now so that we can just fit it all into one window. All right. If I divide 9 by 6, I get a common ratio of 1.5. Now what I'm going to do is confirm by multiplying constantly by 1.5. 6 times 1.5 is 9. 9 times 1.5 is 13.5. 13.5 times 1.5, I'll keep the notation consistent. I use the dot for multiplication instead of the parentheses, but let's keep it the same. Is 20.25. So we have indeed a geometric sequence with a common ratio of 1.5. We are multiplying by 1.5 each time. So our common ratio is 1.5. So here's how it goes. To get the nth term, I do 1.5 times the previous term, which is a of n minus 1. If you know how to write recursive formulas, this should be no issue. And it's a geometric sequence with a common ratio of 1.5 and a first term of 6. Okay? That's all there was to it. There are other ways you could have written it too, similar ways, but this was one of the simplest ways. All right? We're moving on. Last question in this video, number 32. Okay, Robin flips a coin 100 times. It lands heads up 43 times. And she wonders if the coin is unfair. A coin is unfair if it's more likely to land on heads or more likely to land on tails. A fair coin has a 50% chance. Let me come back. A fair coin has a 50% chance of landing on heads and a 50% chance of landing on tails. Doesn't mean that's what's going to happen every time, but that's the overall probability, right? Because there's natural variation. Now she wonders if it's unfair. She runs a computer simulation of 750 samples of 100 fair coin flips. That means that she ran a simulation where the computer did 100 fair coin flips 750 times, and the output of the proportion of heads is shown below. Now if you look, I wish they would have said, but they didn't tell you, it looks like it's an approximately normal distribution, and it is. Not exact, but approximate, because this stuff is never exact, right, in the real world. So the output of proportion of heads is shown below. So we got 60% heads here. That means 0.60, right? 60%. Then we got like somewhere between 32 and 36% a few times. And if you add all these samples up, it's 750 samples. But we don't care about the 750 anymore. And she said they're fair coins, so there should be equal chance of getting heads or tails. This 0.499 is 49.9%. That's fair. It could end up being around that amount. It doesn't always end up being exactly 50%. So on average, 49.9% was heads, which is pretty fair. It's never going to be exact. I mean, it could be, but it doesn't happen all the time, right? So that's consistent with a fair coin, and it should be because it was a fair coin simulation. And now the standard deviation is 0.049. Now, here's what we'll do. First of all, I want to erase all the markings I made. Not all of them, but on the diagram. And then I want to take out my highlighter and let's read the question. Do the results of the simulation provide strong evidence that her coin is unfair? Do they provide strong evidence that the simulation results provide strong evidence that her coin is unfair? Explain your answer. Okay. Before we do anything, guys, since it's approximately normal distribution, first I'm going to minimize me. Remember this. If it's inside 2 standard deviations of the mean, in the 95% confidence interval, then it's probably a fair coin. 43 times out of 100, her proportion is 43%. So I'm going to start off by saying Robin proportion of heads was 0.43. That was the 43%, right? 43 out of 100. Now, we want to see if that would be unfair. To me, it sounds like it wouldn't be. But now I'm going to take this mean plus minus 2 standard deviations, right? So the mean plus minus 2 standard deviations. The mean was 0.499 plus minus 2 times 0.049. That's going to be the 95% range of results, right? So let's see what we get. Let's clear everything out. So I'm going to do 0.499 plus and minus 2 times, I'll start with minus, so 0.401 0.597. So that's what we call the 95% confidence level. 0.401, messy, very bad. So that's 0.401 to 0.597, was it? 597. This is our 95% confidence interval. We're 95% confident that if we flip a fair coin, we should get between 40.1% or 40% and 59.7%. That's basically 40 to 60 heads, right? When we flip a fair coin, this is the range of results we could expect, which corresponds to about 40 to 60 heads. Her 43 heads, or 0.43, lies within this interval. Is the same as 0.430 if I want to write it that way. So do the simulation results provide strong evidence that her coin is unfair? Absolutely not. .43 lies inside the interval. So 43 heads is not unusual when you're flipping a fair coin, all right? And when we say interval, we don't have to state it again that it's the 95% confidence interval, all right? That's all there was. Because we expect that 43% can happen. If we got 80 heads, then it would be unfair and favoring heads. If we got 20 heads, then it would be favoring tails, right? But 40 to 60 heads, 40 to 60 tails, that's pretty fair, okay? Moving along. All right. Oh, that was it, guys. That was it for the part 2. Let me come say goodbye for now. I don't never say goodbye. All right, and I'll make it so that I'm not blocking everything. There we go. Okay, guys, this was part 2 of the June 2019 Common Core Algebra 2 exam. If you have any questions, as always, please let me know. I will respond as soon as I get the chance. If you have any comments, if you have something you want to share with me, like a different way you saw to solve a problem, I'm always interested in seeing your approaches. You guys have like some really beautiful like solution methods and wonderful ideas, and I learn as much from you guys as you do from me. And if there's anything you're concerned about, anything you're not sure about, please feel free to share. And if you want to respond to someone else's comment, of course, guys, keep it friendly, but feel free to do so. And good luck. Make sure you study, get a good night's rest, eat right, hydrate, drink lots of water, get your nutrition up. That's just as important for the mind. Okay, and take care of yourselves. All right? Take care, guys. Bye. Best of luck. You'll do great.